Okay, we're going to be starting number theory now, so yeah.
Okay, hi guys. Today we're going to be covering, the first topic we're going to be covering is prime factorization. So the fundamental theorem of arithmetic states that every single integer can be factored into, its unique prime factors. So for example, if we're going to prime factorize a number like, for example, if we're going to prime factorize something like 296, in order to prime factorize that, we're going to go through each of the prime factors that we know it can divide into. So we'll start off with 2, and then we'll get 148, and then we can do 2 again, we get 74, and we go 2 again, and we get 37. So that means the prime factorization of 296 would be 2 cubed times 37. And in number theory problems, prime factorization is really important because a lot of the times in competition math, whenever you see a math problem or a number theory problem, like 90% of the time you'll probably have to prime factorize the number in order to continue on with solving it. So the next concept that we're going to discuss is bases. Bases also occur a lot in problems relating to number theory. So if you're not familiar with the concept of bases, basically what it is for example, let's say you have a number like 123. This number would be in base 10 because this would be equal to 1 times 10 squared plus 2 times 10, 10 to the first, plus 3 times 10 to the 0th power. And this would be like the normal base system that we use in math. But a lot of the times, questions can also ask you different bases. For example, if we have 123 base 8, then that would be equal to 1 times 8 squared plus 2 times 8 plus 3 times 8 to the power of 0. And, this way, this number would be completely different from this number because we're using a different base system. And something important that you need to know about bases is that any of the numbers, for example, 1, 2, and 3, in a number, it has to be less than the base itself. Because if you have a number that's equal to or greater than the base, the number here can just regroup to the next one. So another thing that I want to cover is the idea of bases that are greater than 10. Sometimes you can have a base 12 or a base 13 or base 16. So in this case, we can have any of the numbers for base 12, let's say, we can have any of the numbers from 0 to 11, but we can't express 10 and 11 as digits. Oh, sorry, whoops. We can't express 10 and 11 as digits. So instead we express 10 and 11 as A and B. So if we have a number that's, let's say we have 1, 2, A, B, 3, base 12, that would be 1 times 12 to the power of 4, plus 2 times 12 to the power of 3, plus 10 times 12 to the power of 2, plus 11 times 12 to the power of 1, and plus 3 times 10 to 12 to the power of 0. So that's basically the gist of bases in general. So now let's go through some problems. The first problem we'll start off with, I'll give you a few some time to read it. Okay, so problem is saying we have some 4-digit number n. So we'll say n is some 4-digit number. A, B, C, and D are its digits. All right. So we're removing the leftmost digit. So this is the digit that we're going to remove. After we remove A, we're going to have B, C, D left as the number. So it tells us that B, C, D, this number right here, is going to be 1/9 of the original number, A, B, C, D. Well, we can rewrite this number as 1000A plus B, C, D. And we can rearrange this equation a little bit, and we get 9 B, C, D equals 1000A plus B, C, D. And we can move B, C, D over to this side. We get 8 B, C, D equals 1000A. So now we can just simplify this. We get B, C, D equals 125A. And keep in mind that A is a 1-digit number. So A is any number from 1 through 9. And we know that B, C, D, this has to be a 3-digit number. So we can't have, so B, C, D ranges from 100 to 999. So we can't have a number greater than 999 in BCD. So let's just go through the cases for A. if A equals 1, then we've got BCD would equal 125, right? And if we have, if we have A equals 2, then BCD is equal to 250. And we can just keep going until we get to a number, an A, that gives a BCD that's greater than 999. And that's when we know that we have to stop. So when we have A equals, when we've got A equals 7, then we have a number that's very close to 1000, but it's not. So that means we've got all of our numbers 1, 2, 3, 4, up to 7. These are possible values for A that give a 4-digit number for ABCD. And so that means we've got 7 cases that work. Yeah, so that would be our answer. If anyone has any questions, just ask it in the chat and then we'll try to answer. Yeah, I'll show the question again. You can always just use the Q&A feature to ask questions if you need to. Okay, well, we're gonna move on to the next question. It's another question that we have to do that involves bases. So it says, I'll give you a few seconds to read the problem. Okay, so we have in base 10, 2013 ends in digit 3. Now we want to convert 2676. All right, so okay, so we want to see how can we write 2013 base something such that, well, no, sorry. We want to write 2013 in some base such that it's going to give a number that ends in 3. So let's say we have some number ending in base B, and then this would equal 2013 base 10. So we know that this digit right here is going to be times B to the power of 0, which just means we're going to have like something, let's say our number is ABCD, right? We're going to have like A times B cubed plus B times, sorry, I should have used a different variable, but whatever. B squared plus C times B, and then plus D. And we know that D will have to be 3 because it ends in the digit 3. So we can just subtract 3 from from 2013, and we'll get a number that is divisible by B. Because after we get rid of this D right here, we'll just have a number that's divisible by B because this expression right here is divisible by B. So let's see, after we subtract 3 from ABCD, then we'll have ABC base B, or 0, base B equals 2010, because we're subtracting 3 from both sides of the equation. So after we know that this right here, we know that this number right here is going to be divisible by, or B right here is going to be divisible by 2010, because this is equal to 2010. Oh, what just happened? Hold on. So we're going to want to go through the numbers that are divisible by 2010. 2010 is equal to 2 times 5 times 3 times 67. That's its prime factorization. And the number of ways to find the number of divisors of 2010 is to take the exponent of each prime and then add 1 to it and then multiply everything together. So we have 2 times 2 times 2 times 2 equals 16. And that's the total number of factors of 2010. But keep in mind that we know that the last digit of the number in base B is 3. And remember earlier I said that when you have something in a certain base, all of the numbers, all of its digits have to be less than the base itself. So we have to have all of our possible bases have to be greater than 3. And so we know that all of the factors of 2010 are greater than 3 except for 1, 2, and 3. So that means we have to subtract these 3 factors from 16. So we get 16 minus 3 is 13. So that would be the number of bases that it can possibly be. Okay, if you want, I can explain it again. So I may have gone too fast. So basically, if we have a number that's like A, B, C, D base B, right? All of these numbers have to be less than B. And in the end, if we take out D, if we take out this digit, then it's going to be this number, this remaining number, ABC0, base B. If we change this to base 10, it's going to be divisible by B because we're multiplying all of the numbers by B somehow. Does that make sense? So if we have A times B cubed plus B times, by the way, these two are different. Sorry about not using a different variable, but C times D and then plus 0. And so this number in base 10, it would have to be divisible by B, which is why we have to find all of the numbers that are factors of 2010. Does that make sense? Okay, I'll move on to the next question. So yeah, just read the question real quick. Okay, so this is a new concept where you change something in base 10 to a number in another base. So for example, if you have like 1000, let's say you have 1000 base 10 and you want to change it to some number base 16. So the way you change it is to keep on dividing until you get 0. So I'll show you what I mean. So we divide 1000 by 16 first and we get 62 remainder 8. And we know, and since this number is not this number is still greater than 16, we just continue. 62 divided by 16 and we get 3 remainder 14. And we get 3, but we still keep dividing. 3 divided by 16 equals 0 remainder 3. So now that we're done, we just take these remainders over here and we just write it in this order. So 3, 14, which is a letter, A, B, C, D, I think might be. Well, it's a letter, and then 8. So this would be our number, base 14. So I'll give you another example. If you're trying to change, let's say you're trying to change 324 base 10 to something base 8, then you would just keep dividing again. 324 would be 40, remainder 4. And then since we have 40 right here, we keep dividing by 8 equals 5, remainder 0. And we keep dividing 5 divided by 8 is 0, remainder 5. So we just write it in this order. We get 504 base 8. So that's how you change from one base to another. If we're going to talk about this problem, then it says it's how many numbers less than 1000 have in base 16 only numbers. So none of the digits are going to be letters. So that means all of the digits are going to be from 0 to 9. None of them are 10 through 15. So in order to do this, we have to first convert 1000 to a number base 16. And I did that earlier. It was 3, 14, 8. Wait, A is 10, B, C, D, E. I think it's 3, E, 8. Base 14, that's 11. That's 1000. So now what we want to do is consider how can we make a number such that all of its digits base 14 are going to be from 0 to 9. So for our first digit right here, we can have any number from 0 to 2. From 0 to 3, because this is our max right here. We have to do a number that's less than this. So any number from 0 to 3 will work because any number here can be from 0 to 9. That would still be less than this. And then digit here can also be from 0 to 9. So now think about it. All of these digits right here, all of these combinations from 399, 398, etc., all the way down, it would always be less than this. And these are all of our possible cases because we can't have something because we can't have a letter. So thinking about this, how do we solve the total number? We just count how many cases are here. From 0 to 3, there's 0, 1, 2, and 3, right? So that would be 4 cases. And then from 0 to 9, there would be 10 cases. And then from 0 to 9, there would be another 10 cases. So we get a total of 400 cases, or 400 numbers in hexadecimal form that are only. And then, but one more thing, we gotta subtract one number, which is 0, 0, 0, because we overcount, because it's asking for positive. So then that would be 400 minus 1, which would be 399, which would be our final answer. So if anyone has any questions, go ahead and ask. Okay, I'll just do a brief overview real quick. So the question basically tells you that you want to find all of the numbers less than 1000 base 10, such that when you convert it to base 16, it turns into a number that has all of its digits that are non-letters. So basically, after we converted 1000 to base, oh sorry, I don't know why I put 14 there, whoops. This should be 16. Yeah, after you convert it to base 16, you get 3E8, and that would be hexadecimal form for 1000. And you're trying to find all of the 3-digit numbers, or not all, just all of the numbers in general that in hexadecimal form are all digits. So we know that from the hundreds digit can be anywhere from 0 to 3, and the tens digit can be anywhere from 0 to 9, and the ones digit can be anywhere from 0 to 9 as well. So that means we have 4 cases here, 10 cases here, and 10 cases here, for a total of 400, but we gotta account for the case where it's 0, 0, 0, so we subtract 1 to get 399. Does that make sense? Oh, how do I convert to 3E8? Basically, I showed you guys the base conversion method where you just keep dividing until you get the remainders, and then you write the remainders in reverse form. So over here, we've got 1000 divided by 16, we got 62 remainder 8, and then we take 62 divided by 16 and we get 3 remainder 14. And we take 3 divided by 16, we get 0 remainder 3. And once we hit the 0, we look at all of the remainders and write it in the reverse order. So we get 3, 14, 8. I don't know why I wrote 14 over there either, but this is supposed to be 16. 3E8. Yeah, so that's how you convert from base 10 to a different base. Okay, next problem, well, next concept we're gonna cover is divisors. And for any number, let's say you have like 100, let's say you have the number 132, and you're trying to find the number of divisors of 132. So basically, as I said previously, you always want to prime factorize this. Well, we know this is going to be 12 times 11, and so we can prime factorize this further. We get 2 squared times 3 times 11. So that's the prime factorization of 132. So in order to find the total number of divisors of 132, you look at all the exponents. We have an exponent of 2 here, exponent of 1 here, and an exponent of 1 here. So to find the number of divisors, all you do is you add 1 to each exponent, and then you multiply all of them together. So we do 2 plus 1 times 1 plus 1 times 1 plus 1. And that's basically how you find the number of divisors. That would be equal to 3 times 2 times 2, which is 12. And that's the total number of divisors of 132. Another example, I'll show you guys another example. If we're gonna do like a number like 32, all it would be 2 to the 5th. So then the number of divisors would just be 5 plus 1 is 6. So that's how you find the number of divisors of a number. And next thing I want to cover is how to find the product. basically, if you have a number, let's do 132 again. Since we already know the prime factorization is 2 squared times 3 times 11. And we know the number of divisors was 3 times 2 is 12. So the product of all of the divisors would be 132 taken to the power of half of this. So half of 12. So the product of the divisors would be 132 to the power of 6. Yeah, that's how you find the number of divisors and the product of divisors. So the last thing I want to mention is how to find the sum of divisors. Let's just use 132 again as an example. So we have 2 squared times 3 times 11. To find the sum of the divisors, it's similar to the number, but it's different. So like you just take each one of these, and then let me just show you what you do. So you take 2 squared, and then you add 2 to the power of 1, then you add 2 to the power of 0, and then you multiply this by take 3 to the power of 1 plus 3 to the power of 0, and then you multiply that by 11 to the power of 1 plus 11 to the power of 0. Then you multiply all of these together, and you get the sum. So basically, for some number, you just take each one of these factors, and then you keep adding, decrease one exponent each time, and multiply all of the sums together. And that's basically how you find the sum. All right, so now let's look at a problem. You can go ahead and read that problem. Okay, so it says that we want to maximize the sum of three factors of 2011. So we know that I times M times O is going to be 2001. So as I said earlier, you always want to you don't have to prime factorize this first, but think about it. If you're trying to maximize the sum, you want to make one of the numbers as big as possible. That's basically the strategy here. You want to make one of the, let's say you want to make I as big as possible, and then make M and O as small as possible. So, but I, M, and O have to be distinct, which means they have to be different. So let's make O 1, because 1 is the smallest divisor of 2001, and it doesn't change its value. So then let's think, we know that 3 is going to be divisible by 2001. So let's make M3, because that's definitely the next smallest divisor of 2001. So that leaves I to be 2001 divided by 3 equals 667. So I would be 667. And this way, you have the maximum total sum of I, M, and O. Because think about it, if you're going to further factorize 667, which I'm not sure if you can, but if you can, then it would give you like 2 smaller numbers. If you're adding smaller numbers together, it's not as big as adding together a big number and then 2 smaller numbers. That's like basically the idea for this problem. So the answer would be 667 plus 3 plus 1 is 671. Does that make sense? Okay. All right, the next problem, you can go ahead and read it. All right, so it's saying we have to somehow express 10 to the power of n as the product of 2 positive integers, and then none of these none of these 2 integers contain the digit 0. So we can factorize 2 to the power of n as 10 to the power of n as 2 to the power of n times 5 to the power of n. And we know that as long as we multiply a 2 and a 5 together, we'll get something that has a 0 in it. So even if we multiply 2 and a 5 together, we'll get 10. That's pretty much common sense. So obviously we don't want to be multiplying 2 times 5 together, and then this side we're multiplying another 2 times something, 2 to the power of something, and then 5 to the power of something, and then 2 to the power of something, and 5 to the power of something. We don't want to split our factors this way, because we know we're going to get a zero, some zero over here and some zero over here. So how else can we split the 2s and the 5s so that we can ensure that at least one, wait, hold on. So let's just pretend that n is going to be like 3, okay? Then if we split it as 2 times, we know that if n is 3, then we want to find some way to multiply 2 numbers together to get 10 to the power of 3. If we split it as 2 times 5 times 2 times 2 times 5 times 5, obviously there will be 0 here and a 0 here, but another way that we can split it would be 2 times 2 cubed times 5 cubed, but it would be 8 times 125, and none of these have a 0 in them, which means like that 3 would not be the answer. So we're trying to find the minimum number that actually has a 0 in the factors no matter how you split it. So we're trying to, so let's see. So the general concept of this is you want to put all of the 2's together and then put all of the 5's together. This way we can avoid having 0 as part of our factor, as part of one of our factors. So let's see, when is the first time that we get a 0 when we keep multiplying 2's? So when n is 1, we get 2's, we get a 2, and then when n is 1, we get a 2, when n is 2, we get a 4, etc. And then we keep going, we get, until n is 10, we get 1024. And this is the first time that we get a 0 as part of our n, as part of our 2 to the n. So right now, our record for the smallest n would be 10, and we're trying to beat this record per se. So let's go with our 5's and see if we can beat the record of n being 10. So if for 5's, if n is 1, then we get 5. N is 2, then we get 25. And then n is 3, we'll get 5 cubed, which is 125. N is 4, we get 625. N is 5, we get 3125. N is 6, we get 15625. N is 7, is 78125. So far, we still don't have any zeros in here yet. So the next one we want to do, we want to try n equals 8, and we get 390625. And so we see that 390625 has a 0 in it. So, and 8 is less than 10, and we're trying to find the minimum number for n. So that means our minimum number for n would be 8. I know this is like kind of bashy, but there's no other way, there's not really a better way to do this, because you're trying to like find where 0 appears in powers of 2 or powers of 5, and you can't really like prefigure that out somehow. So you just have to like bash through all of the numbers. Oh, you want, okay, here's the question. You can also like look through the handout if you want. Okay, if you guys, do you want me to explain this again? Okay, I'll explain it again. Okay, so basically we're trying to find how how we can multiply two numbers together to get a product of 10 to the power of n, right? So, and we know that, and we were trying to figure out a way such that no matter how you multiply two numbers to get 2 to the power of n, they have to have a 0 in one of the factors, no matter how you multiply it together. So in order to do this, oh, whoops, sorry. Okay, so in order to do this, we know that if we like put 2s and 5s together, we'll get, and then we multiply this by another factor of 2 and 5. So if we do 2 times 5 times 2 times, yeah, then we'll have 10, and then we'll have like 10 to the power of 9, and both of these have zeros in them. But if we do 2 to the power of, like, okay, sorry, I messed that part up, hold on. So let's assume that n is equal to 3, okay? Let's assume that like the minimum value of n is 3. So then we want to find two numbers that when you multiply them together, you get 10 to the power of 3. But at least one of the factors has to have a 0 in them. So let's think about it. If I multiply 8 times 125, that would equal 1000, except none of these have zeros in them. So that would be wrong. So 3 doesn't work as n. So we know that n can't be 3 because if we multiply 8 times 125, neither of them have 0, but that's wrong. All right, so but basically we're trying to find what number is the minimum value of n such that when you multiply, no matter how you multiply them, you have to have a 0 in one of them. So basically that's what I did over here, but I'll just do it again. So we're trying to see the first time that you get a 0 in 2 to the power of something, 2 to the power of n. And if we keep going, we get 2, 4, 8, 16, 32, 64, 128, 256, 512, and then 1024. And this, we can see 2 to the power of 10 is the first time that we get a 0 in a power of 2. All right, so then we're trying to beat, so right now we have n equals 10, but we don't know if this is the minimum one yet. So we're trying to beat n equals 10. So in order to beat this, let's look through the powers of 5s. As I said earlier, we have 5 to the first is 5, and then just keep going. I showed you guys the numbers earlier, but the first time that we get a number with 5 with a 0 in it is 5 to the power of 8. We get 390625. And we can tell that in this case, n would be 8. And since we're trying to find the minimum value of n, it would be 8 instead of 10 because 8 is less than 10. Okay, does that make sense? Does that make more sense? Okay, cool. All right, we're gonna move on to the next divisors problem. Go ahead and read that. Okay, so we're trying to find a sum from 1 to n such that it would evenly divide 6n. Well, how many numbers n does that work for? So if I hope a lot of you guys may already know the formula for the sequence for adding the sum 1 plus 2 plus blah, blah, blah up to n. A lot of you guys may know that formula already, but for those of you guys who don't know, it's basically n times n plus 1 over 2. And I'm not sure if we're gonna have time to go over why, but I'll just let you guys know that it's n times n over 1 divided by 2 is equal to that. Okay, so now that we know that, we want to find the number of positive integers n such that this thing divides 6n. And for those of you guys who don't know, that's a symbol for divides. Which also means that we're trying to find the number of integers n such that this expression right here is a factor of 6n. So since both of these have n, we can kind of just cancel them out. We get n plus 1 over 2 has to divide 6. And it logically follows that because n plus 1 has to divide 6, we know that n plus 1 over 2 has to divide 6. We know that n plus 1 would have to divide 12. Okay, So let's think about it. What are the numbers that can possibly divide 12? We have 1 can divide 12, 2, 3, 4, 6, and 12. These numbers can all divide 12. So that's 6 numbers so far that can possibly serve as n plus 1. But we're trying to find n, not n plus 1. So we subtract 1 from each of these for n. So 0, 1, 2, 3, 5, and 11. These are the n values, and these are the n plus 1 values. But we can't have 0 as n, obviously. So the remaining number of integers here is 5 numbers. So 5 possibilities for n. So does that make sense? Okay, if that makes sense, if anyone has any questions, feel free to ask, but I'm gonna go on to the next question. Okay, go ahead and read this. All right, so first we're gonna prime factorize 2010 squared. In order to prime factorize 2010 squared, let's prime factorize 2010 first. We get 2 times 5 times 3 times 67. And so now we got to prime factorize 2010 squared, so we just distribute the exponent. We get 2 squared times 5 squared times 3 squared and times 67 squared. So that would equal to 2010 squared, this right here. We're trying to find how, like if Maya randomly chooses some divisor of this expression right here, then what is the probability that the divisor she chooses is going to be a perfect square? So for those of you guys who don't know, a number can only be a perfect square when all of the exponents are even. So all of these exponents right here, these exponents must all be even in order for a number to be a perfect square. And in order for a number to be a divisor, it also has to be each one of these exponents has to be less than or equal to. So for 2, the exponent can either be 0 or 2, because these are the only 2 even numbers that are less than or equal to 2. And then for 5, it can only be 0 or 2, because these are the only numbers that are less than or equal to 2. And then for this one, same 0, 2, and then this one is same 0 and 2. So we've got 2 choices for our exponent for 2, 2 choices for our exponent for 5, 2 for 3, and 2 for 67. So the total number of divisors that is going to be a perfect square is going to be 2 times 2 times 2 times 2 equals 16. Okay, but we want to be careful because it's telling us that she's choosing 2 distinct divisors. So she's not choosing the same, they're different divisors. So the probability that the first divisor she chooses is going to be, oh wait, we need to find the total number of divisors of this first in order to find the probability. And as I mentioned earlier, to find the total number of divisors, you add 1 to each exponent and then multiply them all together. So you get 2 plus 1 times 2 plus 1 times 2 plus 1 times 2 plus 1, that would be 81. Okay, so now that we have the total number of divisors and the number of divisors that work, the probability that the first one she chooses is going to be a perfect square would be 16 over 81. That would be the probability for the first one. And so since she's already chosen one, the next one cannot be the same, meaning that the next one has to be not a perfect square because it's asking for exactly 1 perfect square. So out of the next one, it would be 80 other divisors that she can choose from, and then 65 remaining, because there's 65 non-perfect squares. That's what you do when you get 81 minus 16. These are the total number of non-perfect squares, and this is out of how many she can choose from. So we get, after we simplify this, we would get 81 over 13, but remember that that order, that we didn't account for the order. So she can either pick the correct one on her first try, or she can pick the correct one on her second try. So we can multiply by 2, and we get 81 over 26 over 81. That's for our final answer. Does that make sense? Okay, do you want me to explain it again? Yes, it makes, okay. All right, I'll just like briefly go over everything I did. So our thought process for this problem would have to be you find the total number of divisors, then you find the total number of divisors that are perfect squares, then you find the probability of getting a perfect square divisor, and you find the probability of getting a non-perfect square divisor, then multiply by 2. Okay, so we found the total number of divisors of 2010 squared. That would just be 3 times 3 times, that would just be this part. 3 times 3 times 3 times 3, that's 81 total divisors. And then the number of divisors that work are going to be 2 times 2 times 2 times 2 equals 16, okay? So that's the number of divisors that work. So that means the probability of getting a perfect square on her first try would be 16 over 81. And the probability of getting a non-perfect square on her second try would be 65 over 80. So then after we multiply that together, we get 13 over 81. But now we have to multiply it by 2 because we have to consider the possibility that she gets the perfect square on her second try. So that's why we get 26 over 81. Does that make sense? Or does that make more sense? Okay. All right, now we're going to move on to our next topic, exponents and factorizations. But basically for this, all I really want to say is that when you have a number that's a perfect cube, all of the exponents in its prime factorization have to be divisible by 3. So what I mean by that is, let's say you have the number 216. 216 would be 6 cubed, so that's why it would be a perfect cube. And if we prime factorize 216, we get 2 times 3 cubed equals 2 cubed times 3 cubed. And so notice that all of these exponents here are a multiple of 3. And this is similar for perfect squares as well. If we have like 144, that would be 12 squared. So if we prime factorize 144, we get 2 squared times 3 whole squared. We get 2 to the power of 4 times 3 squared is 144. And notice these exponents right here are all even. So, and they're also all multiples of 2. So that's why, so that's important to note that whenever you have a perfect something, all of the exponents of the prime factorization are going to be multiples of that number. Okay. So go ahead and read that problem. Okay, so for this problem, we're going to want to prime factorize first, or like put it in the prime format. So we have 25 is going to be 5 squared to the power of 64 times 64 is going to be 2 to the power of 6 to the power of 6 to the power of 25. So that's 5 to the power of 128 times 2 to the power of 150. Okay, but we want to find the sum of the digits. So let's see how we can make it easier for ourselves. Basically, what we would do is 5 to the power of 128 times, oh no, sorry. We can get 2 times 5 together, put them together and put it to the power of 128. Raise it to the power of 128. And then we have 2 times 2 to the power of 22 left. This makes sense, right? Because I'm just taking out the smaller exponent and distributing it to 2 and 5, and then keep, multiplying by the remaining 2 to the power of 22. But the problem says that this is the square, this is actually the square of a positive integer. We're trying to find the square root of this, so you just have all the exponents. So 2 times 5 to the power of 64 times 2 to the 11th. So this is the number that we're actually looking at. This is n, okay? And we're trying to find the sum of the digits of n. Obviously, if we have 2 times 5, we get 10 to the power of 64 times 2 to the 11. And this is just going to be 1 followed by 64 zeros. And after you multiply this by 2 to the power of 11, this, by the way, is 2048. After you multiply 2048 times 1 followed by a string of zeros, obviously we'll just get 2048, 0, 0, 0, 0, a bunch of zeros. So the sum of the digits of this number is just going to be the sum of the digits of 2048, which is 2 plus 0 plus 4 plus 8 equal to 14. Does that make sense? Okay, cool. All right, here's the next problem. Go ahead and read that. Okay, so for those of you guys who might not know what a factorial is, basically if you have a number to factorial, that means you multiply all of the numbers from 1 to that number. So you have 1 times 2 times 3 all the way until you multiply it up to n. That's basically what a factorial means. So let's go ahead and expand 3 factorial times 5 factorial times 7 factorial. That would just give us 3 times 2 times 1 times 5 times 4 times 3 times 2 times 1 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Okay, so now let's try to prime factorize this, because we always want to try to prime factorize stuff. All right, so in order to prime factorize this, we got to go through all of the factors of this, all the prime factors of this. So the smallest prime factor of this would be 2. And let's just count how many factors of 2 are in this. So here's 1. 4 has 2 prime factors, so we've got 1, 2, 3, 4 for another 2, and then 6 has 1, so 5, and then 4 has another 2, 6, 7, and then 2 has another 1, so 8. We would have 2 to the power of 8. There's 2 factors of 2 in this. Now we count the number of factors of 3. So this is 1, 2, 3, 4. Yeah, there's only 4 powers of 3 in this. And next we do the powers of 5, so 1 and 2. There's only 2 here. And then there's only 1 factor of 7 in here. So this would be our prime factorization. Now the question is asking how many factors of this right here are perfect cubes. And as I said earlier, in order for a number to be a perfect cube, all of the exponents have to be a multiple of 3. So let's think. The multiples of 3 that are less than 8 are going to be 0, 3, and 6. That are multiples of 3 that are less than 4 are going to be 0 and 3. The multiples of 3 that are less than 2 is just 0, and same for 7. For 1, it's just 0. So now, in order to find the number of factors of this that are perfect cubes, all we have to do is just find how many cases there are here. So there's 3 cases here, there's 2 cases here, there's 1 case here, and there's 1 case here. So you just multiply it all together, and we get a total of 6. Now, does that make sense? Okay. All right, so I was gonna include another topic in here originally, but like, I don't think we're gonna have enough time to go over it. So like, let me know which question you guys want me to go over again. Okay, you want me to go over the first one? I will go over the first one. So how many 4-digit numbers n have the property? Wait, yeah. You know what? Hold on. Okay, I'm pretty sure you guys know the question already. So basically, all you do is just have a 4-digit number. You take away the first digit, and then the remaining 3-digit number is 1/9 of the original 4-digit number. So we'll have a 4-digit number. Oh, what? We can write our 4-digit number as A, B, C, D. A means the thousandths digit, B means the hundredths digit, etc. And this, after you take away this digit, you're left with this number right here. And it's telling you that this number right here is 1/9 of the whole number. So BCD, by the way, the line over the number means that that's like the number in its form. So BCD is going to be 1/9 of ABCD. Okay, so since we know that A is its thousandths digit, we can rewrite this as 1000A plus BCD. And since this would be equal to that, these two are equal, we can just replace it here too. So we get BCD equals to 1/9 times 1000A plus BCD. Okay. So now if we multiply both sides by 9, we get 9 BCD equals 1000A plus BCD. And now we can just rearrange some things and we get 8 BCD equals 1000A. And now let's divide both sides by 8, so we get BCD equals 125A. So now we know that A is going to be a single digit number because it's a single digit of a 4-digit number. So A is going to range from 1 to 9. And BCD is going to be a 3-digit number, so it's going to range from 100 to 999. Now we're just going to have to go through the cases. If A is 1, then we got the BCD would be equal to 125 because we're just plugging in certain values of A over here to get the BCD value. A is 2, then we get BCD is 250. Yeah, 250, okay. A is 3, we get BCD is 375. A is 4, BCD is 500. Then we got A is 5, BCD is 625. A is 6, BCD 750. And lastly, if A is 7, then BCD would be 875. And if we try to make A equal to 8, then BCD would be 1000, which clearly will not work because we need BCD to be a 3-digit number. So this will not work, and only up to 7 will it work. So 1 through 7 can be the values for A, so that means a total of 7 values for A, for BCD as a whole. Okay, oh, sorry. All right, so what's another question that you guys want me to go over? Okay, the second one? All right, sure. So in base 10, we want the 2013. Okay, so we're trying to represent the base 10 number 2013 in multiple different bases. So we have this number right here, and we're trying to turn it into different bases. So let's say we have some number that's in base B. Let's say we have the number XYZ in base B. This would be X times B squared plus Y times B plus Z times B to the 0, which is just X times B squared plus Y times B plus Z, because B0 is just 1. Okay, so we want Z to be 3 because that's what it's asking you. It ends in 3. So we want XYZ. So we want something that's in the form XY3 equals 2013 base 10. This is base B. Okay, so you know that since 3, you're just adding it to XY0 because it's in the B to the power of 0 place. This is equal to 2013. So we can just go ahead and subtract 3 from both sides. So we get XY0 base B equals 2010. All right, so let's go ahead and expand this left side again. X times B squared plus Y times B equals 2010. And we know that this side is going to be divisible by B because both of these have a factor of B. We can take out the factor. So now we just know that B has to be a divisor of 2010. So now we just have to count the number of divisors that satisfy this. And we do this by prime factorizing 2010 first into 2 times 5 times 3 times 67. And as I said earlier, the total number of factors is 2 times 2 times 2 times 2 is 16. Because each of these, okay, so now let's think, what are the factors of 2010 that can be B? Well, we know that 3, in our original number, we had xy3. So we know that B has to be greater than 3 because you can't have a digit here that's going to be more than the base. So thinking about it, all of the factors of 2010 would work except for the factors that are less than or equal to 3. So there's 3 of them, 1, 2, and 3. So we have to subtract that from our total number of possibilities, which is 16. So 16 minus 3 would be 13. Does that make sense, guys? Okay, so that's basically all I have for today. Make sure you try out the homework packet. It's similar difficulty to what we covered in class today. And if you have any questions, you can always join our Remind. It's at the code is Flashmath, or you can email the email address that Rich sent out earlier. So go ahead and yeah. So now we're gonna move on to combo for those of you guys who are staying.